Welcome to The Explainer. Today, we're going to peel back the layers on the one piece of tech that's behind, well, pretty much everything you're seeing in AI right now. From ChatGPT to image generators, this is the engine that makes it all run. It's called the Transformer, and we're going to break down exactly how this thing works. I mean, it really does feel like magic, doesn't it? You type in a few words, a simple prompt, and boom, out comes this creative, coherent story that just seems to get it. It understands context, nuance. It's incredible. But here's the thing. It's not magic. Not at all. It's a really, really brilliant piece of engineering. Okay, so to really get our heads around this, a good place to start is with a name everyone knows, GPT. It stands for Generative Pre-trained Transformer. Now, generative, that's pretty straightforward, right? It generates stuff. Pre-trained just means it's already learned from a boatload of data. But that T, transformer, that is the secret sauce. That's the part we really need to understand. So what is a transformer? Well, at its heart, it's a special type of neural network architecture that a team at Google came up with back in 2017. And get this, it was originally designed just for translating languages, but it turned out to be so powerful that it became the core invention, the very engine behind this whole AI boom we're in the middle of right now.
So let's get to the fundamental question. How on earth does a computer, which only gets ones and zeros, start to understand something as messy and human as language? Well, the very first step is turning our words into its language, math.
It all happens in three main steps. First, obviously, it takes in your text. Then it chops that text up into little pieces called tokens. A token could be a whole word, like apple, or just part of a word, or even just a comma. And then for the final step, and this is crucial, every single one of those tokens gets converted into a long, long list of numbers. In the biz, we call that list a vector. This whole process of turning words into vectors has a name. It's called word embedding. And the core idea here is absolutely brilliant. It's all about representing words in a kind of geometric space. Just imagine a giant, multidimensional map where words that mean similar things are placed close to each other. So the vector for cat would be near the vector for kitten and feline. What you end up with is literally a mathematical map of meaning. And this is where it gets really, really cool. It's not just about how close words are on this map, the directions between points also carry meaning. This means the model can do a kind of semantic math. It can literally add and subtract ideas as if they were numbers. Okay, check out this classic example. The model learns that the journey on the map from the vector for man to the vector for woman is basically the same as the journey from king to queen. So you can literally take the king vector, subtract the man vector, add the woman vector, and guess where you end up? Right next to the vector for queen. It's incredible. And this works for all sorts of concepts, even things like countries and their food. All right, so our words are now numbers, these vectors full of meaning. Now let's follow them as they take a trip through the heart of the transformer itself. Okay, so you have this whole sequence of vectors, one for each token, and they all enter the first block of the network together. First up is the attention block, and you can literally think of this as a place where the vectors all get to talk to each other to figure out the context. Like, if you say the word bank, are you talking about a river bank or a money bank? The other words in the sentence help it decide. After that, they go to the feed forward block. Here, each vector gets to think by itself for a bit, processing what it just learned. And then, the whole thing just repeats over and over again through many layers. So what's the whole point of this multi-layer journey? It's all about enriching each and every vector with the full context of the passage. Each one is basically soaking up meaning from all the other words around it. So a vector that went in just meaning king might come out the other side meaning something like, a tragic Shakespearean king from Scotland who murdered the last guy. It gets loaded with context. Now, there is a catch. The model can't look at an infinite amount of text at once. It has something called a context size or context window. For an older model like GPT-3, that was 2,048 tokens. That's its short-term memory, basically, the maximum number of tokens it can consider at any given moment. And that's exactly why you might have noticed older chatbots sometimes forget what you were talking about if the conversation got too long. They literally lost the thread. Okay, so we've turned words into math, and that math has talked to itself and gotten super rich with context. But how do we get back to words? Let's look at the final crucial step, making the prediction. After all that intense processing through all those layers, the entire network focuses its attention on just one thing, the very last vector in the sequence. Think about it. That final vector is the one that soaked up the meaning of everything that came before it. It's the culmination of the whole thought process. And it's that one vector that's used to predict what word should come next. But wait, the output from that final vector isn't a word, right? It's just another big list of raw numbers, sometimes called logits. So how do we turn that into an actual word? We use a neat little mathematical tool called the Softmax function. What Softmax does is take that messy list of numbers and transform it into a clean list of probabilities. It gives a score from 0 to 1 for every single word in its vocabulary. And of course, the word with the highest score is the one the model thinks is most likely to come next. Okay, but hold on. If it's just picking the most probable word every single time, wouldn't it be, well, really boring and predictable? How do you get creativity out of that? How does it balance just being a boring prediction machine with being something surprising and original?
Well, the answer lies in a setting you can tweak called temperature. And you can really just think of it as a creativity knob. If you set the temperature to 0, the model becomes completely predictable. It will always pick the word with the absolute highest probability. You'll get a very safe, maybe even boring story. But as you start to turn that knob up, you inject a bit of randomness. The model is now more willing to take a chance on less likely words. This can lead to something much more creative. But there's a trade-off. Crank it too high, and the model can just go off the rails and start spouting complete nonsense.
Okay, so we've walked through the entire process, from words to math and back again. But to truly appreciate what's happening here, we have to talk about scale. Because the sheer size of these things is, well, it's just mind-boggling.
See, the real smarts of an AI model like this isn't in some super complex computer code. It's all stored in these giant tables of numbers. We call these numbers weights or parameters. Here's a good way to think about it. The text you feed it is the raw data, but these weights, they are the knowledge. They represent everything the model learned about language from being trained on a massive chunk of the internet.
So let's put some real numbers on this, using GPT-3 as our example. First up, it's vocabulary. It knows just over 50,000 unique tokens. Those are all the different word pieces it can understand and use to build its sentences.
But that's nothing. The big number, the truly staggering one, is the number of those parameters we just talked about. In GPT-3, there are 175 billion of them. You can think of it as 175 billion tiny little knobs, each one carefully tuned and adjusted during the training process to help it predict the next word. And that is what it takes. That immense scale, that 175 billion parameter brain, is what's needed to find all the subtle, complex statistical patterns hidden in human language. It's why the text it generates isn't just grammatically correct, but actually makes sense, understands context, and can even feel, well, creative. And that really brings us to a deep and kind of fascinating final question to think about. Remember, these models don't understand things the way you and I do. They don't have feelings or experiences. They are just incredibly, unbelievably good at recognizing patterns in data. So the question is this: if something that looks so much like real understanding can emerge just from finding statistical patterns in a sea of data, what does that tell us about what intelligence, or even meaning itself, really is?